Hello, my name is Ryan, and I completed a science fair using this NOAA QFH antenna. First, here is some background information. NOAA currently has 3 satellites that users can listen in on the 137 MHz range. APT stands for Automatic Picture Transmission. These satellites, NOAA 15, 18, and 19, all use APT to send images of Earth to antennas. The APT rate is 120 lines per minute, 2 lines per second. During daylight hours, the satellite sends out 2 pictures simultaneously, one infrared picture on the left and one visual picture on the right. With the use of applications such as WX to IMG, the data can be mapped to see geopolitical lines, enhanced colored images, and even clouds. Before I began the experiment, I used the antenna to listen to satellites as a hobby. I observed that I would have to tilt the antenna to the direction of the satellite to receive a strong signal. The question I asked while conducting this experiment was, how does the angle of satellite elevation affect the reception of APT signals? My hypothesis was that as angle elevation increases, reception of APT signals would increase as well. This is because, as the elevation relative to me increases, I am closer to the signal and would therefore receive a stronger and clearer signal. I predicted that by about 45 degrees of elevation, an APT signal could be heard. To make this antenna, I used multiple materials such as 2-inch PVC, a drill, 1/2 inch PVC, a tape measure, drill bits, a Sharpie, RG6 coax cable, 12 AWG copper wire, duct tape, a soldering iron, a hacksaw, wire strippers, and a PVC cutter. I also used the applications SDR Sharp, SatSat, NOAA APT, and WX to IMG. To build this antenna, I used the instructions from Spaceman Labs on Instructables.com. I constructed the antenna body, and soon I cut the RG6 and soldered the copper wire onto it in both ends to create an infinite balloon. This creates a current flow outside of the cable, which makes the copper wire part of the antenna. Then, I attached this to the software-defined radio and started up SDR Sharp. Using SatSat, I waited for a satellite pass, and then I recorded the entire transmission each time. And I would also record the AOS, LOS, elevation, weather, and time. Once the satellite hit the peak elevation, I would record the decibel peak as well. I did this 16 times with the NOAA satellites. Each satellite is about the same height above Earth, around 850 kilometers, which made it a very negligible variable. To begin, I discovered a strong positive correlation between maximum elevation and signal peak. There are a few outliers, but overall, this is a steady trend upwards. I also looked at the other data, not entirely related to my initial hypothesis. As the length of the satellite path increased, so did signal strength. There is also a loose negative correlation between signal peak and the angle of which the acquisition of the signal was acquired. In conclusion, my initial hypothesis that as elevation increased, reception would also increase was proven. Unfortunately, before the experiment was conducted, a copper wire came loose, so the APT signals could not be heard unless the elevation peak was very high. This is why pictures like this one were the only ones that could be heard. After I discovered this, I reattached the copper wire, and this is the image that I got during a 60-degree pass. If I were to do this project again, to build upon it, I would record many more satellite passes and test in a better location than my attic, such as an open field or my rooftop would be most preferable. I would also add a filter to limit the amount of static received.